Hello dear students, in this video lecture we will solve a problem which is called all pair shortest paths using the dynamic programming approach, and the algorithm which is used to solve this problem called all pairs shortest paths is called the Floyd-Warshall algorithm. So we will study about the Floyd-Warshall algorithm in this lecture. So first of all, let us talk about what is all pairs shortest paths. So you are given a weighted graph G with a set of vertices, set of edges and the weights on the edges. And the problem is to find the shortest path between all pair of vertices in the graph. Okay, suppose your graph contains three vertices A, B and C, and these are the edges, and also we have weights. Okay, suppose the weights are like this. Okay, so the problem is to find the shortest path between all pair of vertices. So what are the different pairs of vertices here? AB, AC and BC. Okay, so these are the different pairs. I think these are the only three pairs with three vertices. Okay, so you have to find the shortest path for reaching B from A, C from A and C from B. Okay, because this is undirected graph, so the shortest path for reaching B from A will be same as the shortest path from B to A. Okay, similarly this will also be same because this is undirected graph, and C to B. Okay, but I have taken an undirected graph here, but this algorithm, the Floyd-Warshall algorithm, this also works for directed graphs. Okay, so you can apply this algorithm on both the directed as well as the undirected graphs to find the shortest paths between all pairs of vertices in your graph. Okay, so what is this algorithm? As I told, it works for both directed and undirected graphs, and it assumes that the graph has no cycles with negative length. Okay, so suppose this is A to B to C. Okay, so like this we can go from A to B, then B to C, then C to A. So this is 10, this is minus 6, this is minus 6. Now this is a cycle, right? A to B to C. And if we want to go from A to B, the length is 10. Then from B to C, the length is minus 6. From C to A, the length is minus 6. So what is the total length of this cycle? It is 10 minus 12, which is minus 2. So this is a cycle with negative length, and the Floyd-Warshall algorithm does not work for the graphs which have such kind of cycles, the cycles which have negative length. Okay, and as I told you in the beginning of this lecture, this algorithm follows the dynamic programming approach to find the shortest paths. Okay, so now let us look at the intuition behind this algorithm. So this is a problem which is solved recursively like other dynamic programming problems. Okay, so there is a base case and there is a recursive case. So first of all, let us talk about the base case. The base case is that the simplest shortest path from vertex I to another vertex j is the weight of the directed edge I comma j. Okay, so let us take the same kind of graph ABC and let us make it directed like this. So this is 4, 5, 3, 2. Okay, so what is the base case? Base case is when you have two vertices I and j which are directly connected by an edge. So if we look at this graph and we talk about A and B, these are the two vertices. So the shortest path is the directed edge. Okay, so there is a directed edge from A to B whose length is 4. Okay, so this is the shortest path. If we take this A to C, then C to B, what is the length of this? This is 5 plus 2. Okay, and it is 7. Yeah. Okay, so this is the base case. This is the shortest path, simplest shortest path. Okay, so it is saying that shortest path from a vertex I to vertex j, and there is a 0 here. At this point of time, let us leave this, let us ignore this. I will tell what does this mean a moment after a moment. Okay, so the shortest path between I and j is the weight of the direct edge between I and j, right? Now let us talk about the recursive case. The recursive case is when you have a number of direct edges in between the path from I to j, like this example, A to C to B. Okay, so we can reach through other paths also except the directed edge. Okay, so in this particular example, this is your A, I means A, J means B, and these are the intermediate edges starting from V1 to Vk, and all of them are distinct. Okay, so in this case we have only suppose V1. Okay, and V1 is C. It means this path is going through C. C is the intermediate vertex. So if you want to find the shortest path between I and j, when you are not talking about a direct edge, then we will write it as I, j, k. So here we wrote 0. 0 means this is a direct path. There is no intermediate edge between I and j. And here we have written k. K means there are some intermediate edges between I and j, and those are V1 to V2 to Vk. Okay, so if we go from I to j through these intermediate vertices, then what is our shortest path? Then the shortest path, this function returns the shortest path from I to j using the vertices from 1 to k in the graph, as I told you, and all of them are distinct and different from I and j. Okay, so what is the shortest path in the recursive case? So the recursive case will take the advantage of dynamic programming nature of this problem. How? So there can be two cases. The first case is that the shortest path between I and j is the shortest known path. What does this mean? So we were talking about I, then intermediate edges were there, suppose V1 to V2, and there are some k number of vertices, intermediate vertices, and then we reach j. Okay, so here we recursively solve the problem. Recursively means before solving this problem, we look at the lower order problem where we consider the path from I to j, but we consider the vertices only v1, v2 to vk minus 1. So this is a simpler problem as compared to the upper problem, and so on. We consider V1 only and then J. There is only one intermediate vertex here, and the simplest shortest path, as I told you, is direct edge. There is nothing in between I and J. Okay, so these are the problems. You can see the recursion here, right? So first we are not including any vertex in between, then we are including V1, then V1 and V2, and so on. Then we are including V1 to Vk minus 1, and then we are including K. Okay, so V1 to Vk. Okay, so we are at this subproblem. So at this subproblem, there can be two solutions. The first solution is, as in other dynamic programming approaches, there were two choices. You can include this vertex Vk, or you can exclude this vertex Vk. Okay, so it depends on the, here we are trying to minimize, we are trying to find the shortest path. Okay, so we will pick the minimum of include Vk or exclude Vk. Okay, so whatever is minimum. And if you include Vk, let us for the time being, let us leave this. Okay, so what happens when you include Vk? Let us first consider what happens when you exclude Vk. Then exclude Vk means you are just referring to the previous subproblem, which is this. Okay, so it means you are considering only the vertices from V1 to Vk minus 1. You are not including Vk. Okay, so you will just copy the solution from the previous subproblem which was solved. The previous subproblem was when you took the vertices from V1 to Vk minus 1, right? Okay, so this is the case which I am talking about. This is, it means you are excluding Vk. Okay, so the shortest path between I and J is the shortest known path. So already already the path which is known to you as the shortest, which is this, you will just copy its solution. Okay, and the second case is, it is the shortest known path from, now you are you decide to include. Okay, so this is about including Vk. So if you decide to include Vk, then it means it is the shortest path from I to k, I to vertex k, plus the shortest path from k to j. Okay, so because this k is the intermediate node, you are taking it as the intermediate node. Okay, so there must be a path from I to k and there must be a path from k to j. So it means there are two subproblems and the solutions to these subproblems are already known. Okay, so we already know the shortest path from I to k, we already know the shortest path from k to j. So we will just copy their solution and then add up. Okay, so now we have both the answers. What is the answer with excluding Vk? What is the answer with including Vk? And whatever gives us the minimum path, the minimum or the shortest path, we will pick that answer. Okay, so shortest path from I to j using the vertices from 1 to k. This k means you are using the vertices starting from 1 to k, is the minimum of the shortest known path by excluding k, right? Because you are using the vertices from 1 to k minus 1 only here. And the second argument is the shortest path including k, where you will find the shortest path length from I to k and then from k to j. Okay, and here the intermediate vertices are from 1 to k minus 1. Okay, because k is the intermediate vertex which you have just picked. Okay, you have not included in the previous paths. The previous paths included only the vertices starting from 1 to k minus 1. Okay, so whether you exclude k or you include k, the paths or the subproblems which you will refer to, they will contain the intermediate vertices starting from 1 to k minus 1 only. Okay, and for a better understanding, let us look at this diagram. Here you are including k. Okay, so k is the intermediate vertex here in the path from I to j. Okay, so when you decide to include it, then your solution or the subproblems are divided into two parts. The first subproblem means you are considering the path from I to k. Okay, I to k, and in the second subproblem you are considering the paths from k to j. Okay, and the intermediate vertices here are 1 to k minus 1. Similarly, here also the intermediate vertices are from 1 to k minus 1. And overall, when you consider this problem as a whole, it means you are considering the vertices from 1 to k. Why? Because this subproblem consists of paths till k minus 1. Similarly, this also consists of the vertices till k minus 1. And when you include k, it means in the overall subproblem, you are also including k along with the other vertices. Okay, so total vertices which you are considering as intermediate vertices are 1 to k. Okay, okay, so now let us look at the algorithm. So initially we have W naught. W naught is the adjacency matrix of your graph with edge weights. Okay, so W0 ij, so each entry of that matrix is equal to the weight. Okay, so because this is the base case which we talked, this is the simplest shortest path where you do not need to further refer to other subproblems. This is the basic subproblem which we are solving at very first instant. Okay, so the base case is this. Here the each entry of your matrix, it will contain the weight of the edge between I and j if it exists, and if the edge does not exist, then the entry will contain infinity. Okay, then we have solved the base case, then we will solve the other problems recursively one by one. So for k starting from 1 to n, so we will include all the vertices one by one. Okay, when k is 1, it means you are including the first vertex only. When k is 2, it means you are including the vertices from 1 to 2. When k is n, it means you are including the vertices from 1 to n. Okay, so you will compute wk at each iteration of k loop, and it will be computed from the previous w, that is previous iteration of k. So it will be computed from wk minus 1. Why? Because if you look at this equation, so here when you are solving it for k, you are always looking at the previous solution, that is k minus 1, k minus 1 here, k minus 1 here. Okay, so everywhere it is k minus 1. So you will solve for wk by looking at wk minus 1. So how will you solve it? You will pick the minimum of the two cases, exclude k or include k. When you exclude k, you will simply copy the k minus 1 iteration solution for I and j, and when you include k, you will copy the solution from k minus first iteration, but it will be for I to k plus the solution for k to j. Okay, so this is the same thing which we discussed in the previous slide. Okay. So this is a simple Floyd-Warshall's algorithm. Okay, and at last you will compute Wn, and this matrix will contain the final weights of the shortest paths for all the pairs. Okay, so to understand it in a better way, let us look at an example. So this is the graph which is given to you. The vertices are 1, 2 and 3, and this is the weight matrix W. Okay, so there are how many matrices? Vertices. There are 3 vertices. Okay, so there will be 3 iterations of the K loop. Okay. 3, not 3 actually, it will be 4, right? We will create 4 W matrices. So the first W matrix is W0. Okay, suppose this is W0. So the W0 will just contain the this is the base case. We are solving the base case here, right? So it will just contain the weights of the edges. So 1 to 1 there is no edge, so it will be not 0, it will be infinity. Okay. Similarly, there are no self loops. Okay, so all the diagonal elements can be infinity. 2 to 2 infinity, 3 to 3 infinity. Okay, then 1 to 2 there is a direct edge with value 4. Then 1 to 3 there is a direct edge with value 11. Then let us look at this row. 2 to 1 there is a direct edge with weight 6. 2 to 3 there is a direct edge with weight 2. Then let's look at the third row. Here 3 to 1 there is a direct edge with value 3, and 1 to 3 there is a direct edge with 1 to 3 there is a direct edge with value 11. Okay, no, 3 to 2, we want to see 3 to 2. 3 to 2 there is no edge, so it will be infinity. Okay, so this is the base case which we have solved, and by looking at the base case we will solve the other cases recursively. Okay, so K will start from 1, 2 and N here is 3. Okay, so let us say K is 1. We are at the first iteration. So we will find W1, right? And these are the vertices 1, 2, 3. Okay. Okay. So W1 to 1. W1 to 1, and K here is also 1. This is I, this is J, and this is K, right? Is equal to minimum of W. Let me use the notation which we used in the previous slide. That is W1 I and J, both are 1, is the minimum of, we will look at matrix W0. W0 IJ or W0 I K, K is also 1 here, I K plus W0 KJ, KJ. So whichever is minimum of these. Okay. So it is equal to minimum of W011. It is infinity. So infinity plus infinity. So it will be infinity. Okay, now let us move to the next cell. This is the 1, 2. Okay. J is 2 now. So only J will change. And J is here. Okay. So 1, 2. If we look at previous case, it is 4. And 1, 1 is infinity plus 1, 2 is 4. Okay. So it will be 4. So if we want to go to vertex from vertex 1 to 2 using vertex 1, what does this mean? There is, you are using 1 as an intermediate vertex. Okay. So from 1 you are again coming to 1, and from there you are going to 2. So and the answer will be same in every case. Okay. So even if you take 3 here, here will be 3, 3 here. So it will be 1, 3 is 11, 1, 1 is infinity, 1, 3 is 11. So answer is still the same. Okay. Okay. So now let us move to the second row. In the second row, we are talking about first 2, 1. 2, 1. Again, the intermediate vertex is 1. Okay. So it is W0 2, 1 or W0 IK, it will be 2, 1 and KJ 1 and J is also 1. Okay. So 2, 1 is 6. 6. 1, 1 is infinity. So it will be same. Everywhere if you try to see, it will be same. 2, 2, it is infinity. So if you change here 2, 2, W22, W22, here also 2. Okay. Then you will see it is infinity. 2, 1 is 6 and 1, 2 is 1 to 2. It is 4. Now it is changing. Okay. So the minimum is 10. Okay. So it means if you want to go from 2 to 2 and you are using 1 as an intermediate vertex, the previous distance was infinity. Now it is saying that it is 10. Is it? Let us look here. 2 to 1 it is 6 and 1 to 2 it is 4. So now we are getting a better distance. Okay. Okay. So now let us move to the next cell 2, 3. It is 2, 3, 2, 1, 1, 3. Okay. So 2, 3 is 2 here. 2, 1 is 6 and 1, 3 is 11. Okay. So minimum is 2. So we will keep 2. Right. Now let us move to the third row. 3, 1. 3, 1 is minimum of W0 3, 1 or W0 3, 1 and W0 1, 1. Okay. Here this is K. Okay. So 3, 1 is 3. 3. 1, 1 is infinity. So 3 will be placed in this cell. Next is 3 2, 3 2. So 3 2 and W naught 3 1 1 2. Okay, so 3 2 is infinity, 3 1 is 3, and 1 2 is 1 to 2, it is 4. So now we are getting a improvement over the previous matrix. It is 7. And if you analyze it, it is what? It is 3 to 2 using vertex 1. So if you want to go to 3 to 2, there was no direct edge. Okay, so we try to go through vertex 1. So first we will go to 1, the distance is 3. Then from 1 we will go to 2, the distance is 4. So the total distance which we are getting is 7 here. And now the last one, 3 3. 3 3 will be minimum of W naught 3 3 or W naught 3 1 1 3. Okay, so 3 3 is infinity, 3 1 is 3, and 1 3 is 11. Again we are getting an improvement. It is total 14. So 3 to 3 you can go through 1. 3 to 1 and 1 to 3. Okay, so this is W1, right? So using this W1, now we will move to the next iteration. We will find W2. Okay, so now let me erase. Now we do not need W naught anymore. Okay, so we can erase it. Now we are at W1, sorry, not W1, we are at W2. It means we have solved this subproblem using finding the shortest distances using vertex 1. Okay, now we will also include vertex 2. Okay, so we will see whether we can find, if we include vertex 2 also, whether we can find better distances, shortest paths or not. Okay. Okay, so here we will fill W2 matrix and it depends on W1 matrix, right? And first it will be W11 and now our K will change. The intermediate vertex which we are considering is 2. Okay, and we are looking at W1. It means we are also considering the shortest paths which were found by using vertex 1. Okay, and here also we will look at vertex 1. Okay, so it is 1 1. So we will look at W11 and W1 1 to 2, W1 2 to 1. Okay, so W11 is infinity, W12 is 4, and W21 is 6. Oh, we are getting a better path from 1 to 1 and the distance is 10 using intermediate vertex 2. Okay, so let us look at it. It is 1 to 2. Intermediate vertex is 2. 1 to 2, 4. 2 to 1, 6. Right? Okay. Now 1 to 2. Now J is 2. J is 2. Okay. So 1 to 2, the distance is 4. Here also it is 4. And 2 to 2, the distance is 10. Okay, so we have already the minimum. We will not consider using vertex 2 here. Okay, so 1 to 3 now. J will change. Okay, 1 to 3, the distance is 11. 1 to 2, the distance is 4. 2 to 3, this is 2. Okay, so the minimum is 6. So again we are improving. Yeah, we are getting a better path using vertex 2. Okay, so if we want to go from 1 to 3, we can use vertex 2. Okay, so 1 to 3 intermediate vertices. Already we have considered one vertex 1, right? Because we are considering W2 here, W1 here, and now 2 is also there, and the final destination, that is J, is 3. Okay, so we are not sure in W1 whether it was included or excluded, but we have considered it. Okay, we have evaluated this option, right? So what was the answer? The answer is 6. Okay, so I think we excluded this because there was no path, direct path from 1 to 1. So when we go from 1 to 2, the distance is 4, and 2 to 3, the distance is 2. So that is why we are getting 6 here, right? Okay, so this cell is complete. Now let us move to the next cell. First, next row, 2 to 1. So here I is 2 and J is 1. 2 and 1. Okay. So 2 comma 1 is 6, 2 comma 2 is 10, 2 comma 1 is 6. So we have already got the minimum. We will not change it. Then 2 comma 2, J is 2. Okay, so 2 comma 2 is 10. It will be 10. 2 comma 2 is 10. Okay, everywhere it is 2. We have already got the minimum. Again, we will not consider vertex 2 here. And because we are in row 2 and we are considering vertex 2 as the intermediate node, no value will change in this row because there are no self loops, right? 2 to 2, there is no path, right? So all the cell contents, all the contents in this row will remain same as W1. Okay. Similarly, if we consider this also, the answer will not change. 2, 3 is 2 and 2, 2 is 10, 2, 3 is 2. So as I told you, the answer will not change here. Okay, and now let's go to the last row. This is first 3 comma 1. I is 3 and J is 1. I is 3, J is 1. Okay. So what is 3 comma 1? It is 3. 3 comma 2 is 7 and 2 comma 1 is 6. So we have minimum already. Now let's move to 3 comma 2. Okay, 3 comma 2 is 7 and 2 comma 2 is 10. So again no change. 3 comma 3. 3 comma 3, here 3. Okay, so 3 comma 3 is 14, 3 comma 2 is 7 and 2 comma 3 is 2. So now we are getting minimum 9. It means if you want to go from 3 to 3, let us consider vertex 2. So vertex 1 was already considered in matrix W1. Now we are also considering vertex 2, and then there is 3. Okay, so was there any path from 3 to 1? There was a path and its distance was 3. Then from 1 to 2 there is a path whose distance is 4, and from 2 to 3 there is a path whose distance is 2. So total is 9, which we are getting here. Okay, so it means in W1 this vertex 1 was included, right? Okay, so W2 is also complete. Now we can move to the last iteration of k loop, where value of k is 3. So it means now we are considering all the vertices. In W2 we consider the vertices. Let me write the complete story here. In W0 we did not consider any intermediate vertex. In W1 we considered vertex 1. In W2 we considered vertex 2. But here we looked at vertex 1. So indirectly we also considered vertex 1. And in W3 we will consider vertex 3. But here we will look at the solutions obtained in W2. So it means we are including all the vertices 1, 2 and 3. Okay. So it is now W3, because we do not need W1 anymore. Okay. So let us first go to the first row, 1 and column 1. So W11, and here 1, here also 1, and k is 3 here. Right? Okay. So W11, and here we will look at W2. Yeah, we are finding W3, so we will look at W2. Okay. So W211 is 10, W213 is 6, and 31 is 3. So we are getting a better path from 1 to 1 by considering vertex 3 also. So what is the path? 1 to 1. 1 to 1 to 2 to 3. So we are considering all the vertices from 1 to k, and this is I and this is j. Okay, so 1 to 1 there was no path, so we excluded it. 1 to 2 there was a path whose length was 4. 2 to 3 there is a path whose length is 2, and 3 to 1 there is a path whose length is 3. Okay, so the total is 4, 5, 6, 7, 8, 9. So which we are getting here. Okay, now let us go to the next cell. Now j is 2. W12 is 4, W13 is 6, W32 is 7. So we have already the better path. So we will not include vertex 3 here. Now let us move to the last cell in this row, 1, 3. So j is 3. Here also it is 3. Okay. So W13 is 6 and W33 it is 9. So again no change here. Now let us move to the next row. The cell is 2, 1. W2, 1. So here 2 and here it is 1. 2, 1 is 6. Again is it? Yeah. And then 2, 3 it is is it 2 3? Yes, it is 2 3. 2 3 is 2 and 3 1 is 3. Okay, so we are getting a better path, 5. So 2 to 1 we are getting a better path, 2. We have considered all the vertices here and 1. 2 to 1. 2 to 1 there is a path with length 6. We do not know whether we consider vertex 1 or not. Let's move to next. 1 to 2 there is a path with length 4. 2 to 3 there is a path with length, I think it will not be considered. Why? Because the path which we are getting has length 5 and it can be obtained by not considering this vertex. Okay, so also 2 to 2 there is no direct path, so this will also not be considered. So 2 to 3 will be considered. 2 to 3 the path length is 2 and 3 to 1 the path length is therefore which we are getting a 5 here. Okay, so you can look at the previous words, matrices W0, W1, W2 to find whether in those matrices, these vertices, whether in W1 1 was considered when you were finding the path from 2 to 1, whether in matrix W2 2 was considered when you were finding the path from 2 to 1, and similarly in W3, yes, we know we have considered 3 in finding the path from 2 to 1. Okay. Okay, now let us move to 2 comma 2. Now J has changed to 2. 2 comma 2 is 10 and 3 comma 2 is 7 here. So we are getting a better path, right? Okay. So now you are getting a better path here, and next let us move to 2 comma 3. It is 3 now. 2 comma 3 is 2. Again it is 2 and 3 comma 3 is 9. So we have already the better path. We will not change it. Okay. And then we reach the last row. Here we are including vertex 3 for considering the paths from 3 to 1, 3 to 2 and 3 to 3. And the answers in this case will be same. Okay, 3, 7 and 9, and you can verify it yourself. So this is our Wn, and now it is giving us the all pairs shortest paths, right? So it is giving us the shortest path between 1 and 1. It is giving us the shortest path between 1 and 2, 1 and 2, yeah, 1 and 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So these are the different pairs, and it is giving us the shortest paths between all the possible pairs. And you are recording, we are recording only the distances here, right? We can create another matrix which can record the paths also. Okay. So I leave this as an exercise. So I encourage you that you solve this problem again yourself, and in that solution, in your solution also records the paths. Paths when you are considering W1, what is the path? When you are considering W2, what is the path through which you are getting a particular distance? Similarly for W1, record the path, W2 record the path, for W3 also record the path. So in W3 you will also get the shortest paths, right? Okay. So finally let us look at this algorithm. So here we are creating a matrix W n plus 1 n plus 1. Why n plus 1? Because here we are starting the I loop from 1. Okay. So initially, we will initialize all the values in W matrix to infinity, whether or not there is an edge. Okay, then we will consider all the edges, and we will change the entries I and j wherever there is an edge between I and j. So here we are forming our W naught, and then the scale loop is running from 1 to n. So iteratively we will consider all the vertices starting from 1, then 2 till n. Okay, and for each iteration of k loop we have to iterate over the entire matrix row wise. Okay, so therefore we need I loop and j loop, and at each cell we are making a decision. What is that decision? Decision is that if your entry wij, which is already there, we are looking at the past here. Okay, at the previous iterations results. If the previous iterations results are greater than this thing, which is including k. This option is including k. So if you include k, right, that is you are considering the path from I to k plus k to j. Okay, so you are looking at the previous entries from I to k and k to j and adding them. If they are smaller than the value which is there at I and j, then you will change it. Okay. So this is a simple algorithm, and let us look at the complexity. So here this is the loop which is running n square number of times, and here also we are looking at edges, and if it is in the form of adjacency matrix, so you have to look at n square number of cells, and here we have 3 loops, and these 3 loops, each of them is running n times, so it overall it will take time equal to order of n cube. So overall we can say that the complexity is order of n cube. And what about the space complexity? So we are creating a W matrix here, and the W matrix size is n cross n. So this is the time complexity, order of n cube, and the space complexity is order of n square, because you are creating a table or a matrix of size n square, right? So this is all about the Floyd-Warshall's algorithm, which is based on dynamic programming approach. Thank you.